Namaskar, welcome to CEC Live Lectures. I am Monad Lakha, Assistant Professor, Department of Computer Science, Aryabhat College. Today the lecture is on operating system processes. Just a brief overview, we will be talking about just an overview of what an operating system is and its goals, and some operating system developments like multi-programming, time sharing and real-time systems. We'll be defining what are operating system processes, what was led to the need of operating system processes, discuss in detail what are the process states, how the scheduling of processes is done by the schedulers, your short-term, long-term and medium-term schedulers, the various operation on processes like process creation and process termination. And in the end, we'll conclude with taking the examples of the system calls for process management in Unix. So what is an operating system? An operating system is an interface between a computer user and the computer hardware. It controls the execution of various programs. For example, Microsoft Windows, Linux, Ubuntu, Apple iOS and the Google Android, which has become very famous with your touchscreen devices like your smartphones. The operating system is the one program running at all times on the computer. This is usually called the kernel. So not the complete part of the operating system, but a part of it is running at all times, and this is called the kernel. An operating system is a resource allocator and a control program. The basic goals are to execute user programs and make problem solving easier, to make the computer system convenient and more suitable to use the computer hardware resources in an efficient manner in an easy to use format. These OS goals are defined before the design of an operating system begins. So these are based on the way the system is going to be used. The hardware is designed and chosen based on the operating system goals. So just like when we do any software development, first we need to know what are the requirements of the systems, what are going to be the functionality of the system, and based on that we then define what should be the underlying hardware in this particular case for your operating system design. Now the various computer system developments that happened, now these are all historical events, and these basically have dealt significantly in terms of how the operating systems have worked, how the operating systems have been designed. So one of them is the multi-programming concept, and this allows multiple programs to reside in the memory. So when one program was completing its I/O, the processor could execute another program that was residing in the memory. Otherwise, if multi-programming was not there, what used to happen was that there was only one program which was in the memory. The CPU had to sit idle while that particular program went in for I/O. So by using multi-programming, it increased the average resource utilization and throughput. The CPU was more busy doing tasks for another program while the first program went in to do I/O. Throughput is basically the amount of work done or the amount of processes executed per unit time. So time sharing is another concept. It is a specialized case of multi-programming environment in which the processor handles multiple interactive jobs. Now in this, the processor time is shared among multiple users who simultaneously access the system through terminals. The OS interleaves the execution of each user program in short bursts or time quantums of computation. Now you would think that this would basically make one user wait while the CPU is processing instructions for another user, but that does not happen. Due to the comparatively slower human reaction time, the response time for time-sharing system is similar to that of a dedicated computer. Now, in real-time systems, these are dedicated systems that need to adhere to defined guidelines. Now, what are user mode and kernel modes? So we know that we were just discussing that when you have say multi-programming and time sharing, which is a specialized case of multi-programming, we allow multiple programs to reside in the memory. Now along with that, the operating system programs are also running. So simultaneously we have both user programs and the operating system programs. They are residing in the memory. So for proper execution of the system, a mechanism to distinguish the execution of the user program and the execution of the operating system is required. So for this, a hardware support was developed to make this distinction. A dual mode of operations was defined. One is your user mode and your kernel mode. User mode, so basically it was a hardware, it was just one particular bit, and if the program was in a user mode, bit would be 1, and for kernel mode the bit would be 0. So the dual mode of operation allows the operating system to protect itself and other system components from malicious user program. So some machine instructions, when executed by malicious users, say through malicious programs, can harm the system. So these critical instructions are designated as privileged instructions. So obviously we cannot have any program, user program, to execute these privileged instructions. So these privileged instructions can be executed only in the kernel mode. So when a user program needs to call a system call to execute a privileged instruction, the system call changes the mode to the kernel mode, that means makes the mode bit as 0, and after completing returns the call and resets the mode bit to 1, which is the user mode, and then the program basically executes in the user mode. The user program is executing. So what led to the concept of processes? So all the things which we have discussed just in the previous section, we have this basically led to the concept of processes. Now, the multi-programming, time sharing and real-time systems cause problem in timing and synchronization. For example, multi-programming, processor had to switch between the various programs in the main memory, because we just said that we want multiple programs in the memory so that the CPU could execute one program while the other program is going in for I/O. Same with the time sharing environment, it responds to the needs of the multiple users. So again, there will be multiple programs corresponding to the multiple users, and the CPU is shuffling between these multiple programs. So what led to the concept further? Like in real-time system, the response time had to adhere to these very strict time constraints. So interrupts would stop the execution one program and the processor would start executing another program. The partially executed program had to resume from where it had stopped. So this condition or this state of the process which was partially executed, that had to be saved. So interrupts, so every context switch required that the program specific information of the partially executed process be saved, and this led to the concept of operating system processes. So each execution of the program created a process which had information regarding the details of that process. So for every time the same program, it can be executed multiple times. For example, if I have my Word application, I can have multiple instances of that running in terms of different Word documents. So for and each of these execution instances would be called a process. Each process would have its own information, own unique information, and would have a PCB or a process control block which would be saving information specific to this particular process. So basically processes are central to the design of an operating system. These are required because the main idea is that we want resource sharing. These could be your physical resources like your hardware or your logical files which have to be shared amongst various processes. The computation speed also is increased if we have the concept of processes, because we are taking the advantage of multiple programming, and it is also helping us maintain the modularity of the system. Now, what is a process? A process can be defined as an instance of a running program, a program in execution, an entity that can be assigned to a processor and that can be executed on a processor. So program is a passive entity which is stored onto your disk. For example, it is your executable file, and your process is your active entity. So your program becomes a process when the executable file is loaded onto the memory. Now the idea is, when is the particular file loaded onto the memory, when does it become a process? So the process needs a lot of resources. Once we have decided that the process has been created, it has to be created, it has to be loaded into memory. Obviously, it needs a lot of resources so that it can execute efficiently. So we need your CPU memory. It needs I/O devices to be through which it interacts. It needs file and initialization data. Now these resources, which have been allocated to a process when it is loaded onto the memory, are basically reclaimed when the process terminates, and this task is done by the operating system. So typically systems have many processes. You have users and operating system processes which are running concurrently, and once we want to start a particular process or you want to execute a particular process, there are multiple ways in which you could do it. First of all, we could use a command line interface, type the command which will execute a program. So depending on what particular program that you have to execute, you will have a different command. For example, if I have to run a Python file, I will, on my command terminal, I would just type Python, which is basically identifies by, it will call the installed interpreter of Python, and then space and the name of the Python file, and this will start executing it. A process corresponding to that particular Python file will be created. Another way is by using a graphical user interface. So if we, in a graphical user interface like in Windows we have, and these days many operating systems give you that graphical user interface, we move the mouse over the name of the executable file, or it could be an icon, and then we just click on that particular file name or icon, and that file starts to execute. That means a process is creating. Now these days we are more familiar with our touch screen devices, especially our smartphones. So in this case the icons would be on our screen, and we just have to touch the particular icon to start that particular program. So that means it's a process that would be initiated. So once a program, one program can have several processes. So this is how the process basically looks in the memory. You have the various text, which is basically the program code, some data specific to that particular process, and then your heap and your stack, which are basically variable size processes data. The program code, which is also called the text section. Then you have the currently activity, which includes the program counter and the program registers. They are also stored in this particular process. Then you have a stack, which contains temporary data. You have certain function parameters or return addresses of local variables, which are stored onto a stack. You have a data section, which contains global variables, and a heap, which contains memory which dynamically is allocated during runtime. Now we had just talked about process control block, or a PCB. So a PCB is a data structure which has all the information associated with the process whenever a process is created. That means whenever a new process is created. This is stored in the memory. This data structure is called the process control block. It is also called the task control block. The architecture of a PCB is completely dependent on the operating system and may contain different information in different operating system. So obviously, if the operating system has been designed in such a manner that the PCB stores a lot of information, so obviously it will be a larger data structure. Now, what are the particular attributes of a process, or what is the information that is stored in your particular process control block? You have information like your process attributes, the process states, the program counter, the CPU scheduling information, and so on. Process attributes specifically are your process ID. Every process, whenever it is created, a system generated number is given to that process so that it can be identified till the lifespan of that particular process. So this is called a process ID or a process identifier. And information regarding the parent of this particular process is also maintained, and which user created this particular process, that is also important to maintain. What is the parent of a particular process? We will just see subsequently. Now, there are various states in which a process moves. you have your running, your waiting state, and we will this information has also to be stored in your PCB. Since the process can be stopped in between its execution, the state of that process has also to be saved. So basically your program counter and the values of registers also have to be saved. So program counter, as you are aware, stores the location of the instruction that has to be executed next. The CPU registers are the contents of all the process registers which will contain the information about the partially executed processes. Now, CPU scheduling information, each process may be given a particular priority. So that information, any other information regarding the resources, what are the scheduling queues that are there, would also be maintained in the PCB. Memory management information like what is the memory which has been allocated to this particular process, what is the starting address of that memory, what is the ending address of that memory, all that information is stored in the PCB. Accounting information like the amount of CPU use, the clock times elapsed since the start of execution, time limits, these are also stored in the PCB. All this information can be used further to find what was the total execution time of that particular process. I/O status information like what are the devices allocated to the file, what are the list of open files are also maintained in the PCB. This is an example of a process control block. Here you have the process state, a unique process number, the program counter value, the register values, the memory limits of the assigned memory location for this particular process, a list of open files, and so on. Now, apart from your PCB, since there can be so many processes which are running simultaneously, that means they are in the memory simultaneously, we also have to have an easy way to access these PCBs. So here the concept of process table comes into the picture. The operating system maintains pointers to each process's PCB in a per user or a system-wide process table. The process table allows for quick access to the PCB. So if you have say 10 or 20, which is a very small number of processes which are in the memory, there would be that many corresponding amount of PCBs. But if you want to access the PCBs very quickly, you will have a process table which would have the beginning address of say all the individual PCBs. This could be maintained per user. The process table could be per user. That means for every user, whatever are the PCBs or what corresponding to the processes that this particular user has initiated, it could be list according to that, or the process table could be a system-wide process table. So when a process is terminated, the operating system removes the process from the process table, so the entry of the process from the process table, and frees all the process's resources. So that is why it is important that the process ideally should terminate in a normal manner. So all these tasks of taking the memory back, the operating system taking all the resources back can be done. Now what are the process states? So as a process executes, it changes state a number of times. So the first state is your new. The process is being created, it is admitted to the system, it is in the new state. The running state, the processor is executing instructions of this particular process. The waiting state, the process is waiting for I/O or some event to occur. The ready state, the process has all the resources that it needs, it is waiting to be assigned to a processor. And the terminated state, the process has finished execution and will exit the system again by a normal or abnormal termination. Now if you see this particular state diagram, as you can see on the top left, it is in the new state. So in the new state, the particular process is admitted to the system. By default, after the new state, when the process is admitted to the system, it will come in the ready state. All the process is ready, it is all the resources has been allocated to it. But since there are multiple processes residing in the memory and CPU can execute only one particular process, all the processes wait in the ready queue. The scheduler dispatcher will select one particular process, and that process state would change from the ready to a running state. Now there are three scenarios in which the process can come out of the running state. First of all, that there is some external interrupt which has caused the process to stop running. In this case, the process could have continued to execute. It does not have to wait for anything, so it goes back into the ready queue. In another scenario, the process basically needs a particular IO, or it is waiting for some event to occur. So in this case, the process will go in the waiting state, and after this wait is complete, that means the IO is done or the event has been completed, it will go into the ready state. And this will keep on going. That means the process will be shuffling between your ready, running, and then from the running to either the waiting or the ready state until it completes its execution. And finally, once the process has completed its execution, it will exit the system and the process would be in the terminated state. Now, various mechanisms are required to basically decide what process has to be brought into the memory, what particular process has to be selected by the CPU, and so on. And that is why scheduling of processes is important for the operating system. So to maximize the CPU utilization, the operating system quickly switches processes onto the CPU for time sharing. So that means the different processes are sharing the CPU time. The process scheduler selects amongst the available processes and allocates it for the next execution on the CPU. The operating system maintains scheduling queues of processes. So you have a job queue. It is the set of all processes in the system. So that means when does a particular program become a process? When someone has initiated or executed it. So there will be a job queue, and it will be a list of all the processes which are in the system which want to enter into the memory. Then is the ready queue. Not all the processes which are in your job queue, they can enter or they can be loaded onto the main memory. Only a select few, depending on the degree of multiprogramming, are loaded onto the main memory. So the ready queue is the set of all the processes residing in the main memory. These are ready and they are waiting to execute on the CPU. So it's just waiting that the scheduler will select it and it will go from the ready to the running state. Now we also have device queues. We know that every process may be going in for certain IO, or it may be accessing a file which is on a particular device. So that device also, you can have multiple processes sharing these various devices, so they will also queue up for these particular devices so they wait in those particular queues. So your device queues, this is a set of all the processes waiting for a particular IO device. So the processes migrate amongst the various queues. So as you can see in this particular diagram, the various queues are highlighted. On the top is your ready queue. So as you can see, each process is shown by its PCB, and the different PCBs are linked together within a queue by using a linked list. In the same way, you have different queues for the different devices. So these processes basically move between and the corresponding process control blocks move between these particular queues. Now, when we are talking about the different processes, so as we can see, we have just discussed, when a process basically enters a particular system, it will come in the ready queue, and when it is selected by the scheduler or dispatcher, we will call it the CPU scheduler. It will be given the CPU, it would be in the running state. Now again, either it can terminate or it waits for certain IO. It can also wait for a particular time slice. There is scheduling algorithm like a round robin scheduling algorithm, in which in a time sharing system there are so many processes which are in the memory. Each process is given a particular time slice. So that particular time slice is up, the process cannot keep running, it will go in the ready queue. Then we could also have a scenario in which the process basically forks a particular child, and then a new child processes are created. So that also will go in the ready queue. Process could also be waiting for some event to occur. So again, it will be waiting for these interrupts to occur. So once the IO is complete, once any wait that event has occurred, which has due to which there was an interrupt, those are complete. All the particular processes, they will go back in the ready queue. Now, what are the different schedulers? Okay, so we have our short term or your CPU scheduler. This basically selects which process should be executed next and allocates the CPU. Sometimes it is the only scheduler in a system. The short term scheduler is invoked frequently, basically invoked milliseconds, or could also be invoked for other seconds. So it should be fast. So the short term scheduler or the CPU scheduler selects which process should be executed next and allocates the CPU to that particular process. Sometimes it is the only scheduler in the system, and the short term scheduler is basically invoked say in milliseconds, and after every few milliseconds. But with the faster processors that have come into being, the short term scheduler can also be invoked say in nanoseconds, and hence it should be very fast. The next are your long term schedulers or your job schedulers. These select which processes should be brought into the ready queue. So the long-term scheduler is invoked infrequently. That means it will be in seconds or minutes when it would be invoked. So it can afford to be slow. This scheduler controls the degree of multiprogramming. Now, what is the degree of multiprogramming? It is the number of processes that can reside in the main memory. So that is defined as the degree of the multiprogramming. The operating system basically has to work according to the degree of multiprogramming, and at the time of designing an operating system, it would be defined what the degree of multiprogramming is. So you cannot have processes which are more than the degree of multiprogramming. For example, if I say 10 is the degree of multiprogramming, you cannot have more than 10 processes in the memory. But at the same time, sometimes it may be required that you have to maintain less processes in the operating system because there is too much load on the CPU. So a process can be either an IO bound process, that means it spends more time doing IO rather than computations. So these will have many short CPU bursts because of the fact that it is repeatedly going in for IO, especially for say interactive systems. In that case, it will do some computation, then ask the user for some information, so that means it will go for IO, then it will come back with that information from the user, do some bit of computation, and then go in for IO. So that's why your IO bound processes have very short CPU bursts. You could also have a process which is CPU bound, that means it spends more time doing computations. So these will have very few long CPU bursts. So what a CPU bound process essentially does is, it does not require much IO as compared to say your IO bound process. So in this case, it will keep on executing or on the CPU until it requires that IO, which is not so frequent. Then once that IO is complete, it will be, and it is given the CPU, it will again have a long CPU burst. So for CPU bound jobs, we have fewer CPU bursts, but these CPU bursts are of longer duration as compared to your IO bound processes. So the long term scheduler, since this is responsible for bringing the processes in the memory, it should have a good mix of, it should decide a good mix of IO bound and CPU bound processes. Now sometimes the degree of multiprogramming cannot be maintained. For example, we cannot have say 10 programs in the memory. So in that case, what we need to do is we'll have to remove some partially executed programs from the memory. So here is the role of the medium term scheduler. So the medium term scheduler, it removes a process from the memory, stores it onto the disk, and when the system is free, it is not overloaded, and we can increase the degree of multiprogramming, it brings it back in the disk to continue it execution. So taking a partially executed process out of the memory is called swapping out, and bringing it back in is swapping in. Sometimes a process may not be swapped out just to reduce the degree of multiprogramming. It could just be that the other processes which are in the memory, they require more memory, and you would have to basically decrease the remove some processes from the memory. That means swap out some processes from the memory, so the other processes can get more memory, because you know that the memory or the primary memory is limited. Now, taking this picture into account, if we see this picture, as you can see the ready queue, the center arrow basically shows the entry into the ready queue. That means the first time the particular process enters into the ready queue. So here is the role of your job scheduler. All the processes which are in the job queue, they are in the new state. They are then selected according to the specific jobs which are selected from your job queue. They are picked up and they are put into the ready queue. The state also changes to ready. Now these particular process would then be allocated the CPU. So it is the CPU scheduler or the short-term scheduler which will make this decision as to which process should be picked up from the ready queue. Now this process will continue to execute until it terminates, that means it ends, or there is some IO or some waiting queue that is there, or it could directly go in the ready queue due to some interrupt, as we had seen in the previous figure, and once that a particular IO is complete, it goes back in the ready queue. And as we were just discussing the concept of your medium term scheduler, sometimes you have to remove a partially executed process from the memory. So in that case, the CPU from the running state, that particular process would be taken out, it would be swapped out, and it may not just be in the running state, it may just be in your ready queue. It may be swapped out and it is pushed onto a place in the hard disk, and there's a whole part of the hard disk which we call as the virtual memory, which stores all these partially executed processes, and then when the system stabilizes and this new the processes which were swapped out, they can be brought into the memory. Again, the medium term scheduler selects amongst them and then brings them into the ready queue. Now virtual memory is very important, and it helps us to actually accomplish more in terms of executing more programs. So even due to the limitation of the primary memory, we are not restricted by the size of the RAM. So we extend the memory and use a part of your hard disk, configure it as a virtual memory, so your partially executed processes can be swept out and put in the virtual memory, which is actually physically part of your hard disk. Now an example of how does scheduling happen in mobile devices. Now we have to remember that mobile devices are limited in terms of the size, in terms of the battery that they have, the size of the battery, the weight, the screen size, and so on. So with all this limitation, we are also limited by the other hardware as to what RAM or what processor and all that. So some mobile systems allow only one process to run and other processes are suspended. Like in earlier versions of iOS by Apple for your all the iPads and iPhones. So that is the particular operating system that runs is your iOS. So in this, it only allowed, the earlier iOS only allowed one processor to run and the other processes were suspended. Now what we had discussed in the process state, we had discussed process state in which we have 5 states, but there are various literature which are available which talk about the suspended and the block stage, which are basically variations of your waiting states. Now your single other iOS examples are in the later versions of iOS, which we are coming today. You have a single foreground process. It is controlled by a user interface. So that means the program that is running, the process that is running, which is active on my, say, mobile phone, that would be my foreground process. Now there can be multiple background processes which are running. So but the multiple background processes, they remain in the memory in the case of your particular latest iOS, and they are running, but they are not on the display, and they have certain limit in terms of that there's a short task. They have to be receiving notification of events. There may be specific long running tasks like audio playback. So it's not that in the environment when we want multiple programs to be running, user now wants that I should be able to say hear my audio file, at the same time I can work on my Word document on my mobile phone, or I can access my say WhatsApp chat. So in this case, whatever is active on the screen, for example my WhatsApp chat, that would be my foreground process, and the background process would be your audio playback. The application would be running in the background. So in this case, you can have multiple processes which are running simultaneously, the foreground and the background processes. This is the case of your iOS, your Apple devices. Now, for example, in Android is another popular operating system when we talk about your touchscreen devices like your mobile phones. So the Android runs foreground and background processes, but they're not limits just like you have in iOS. The background processes use a service to perform tasks. The service can keep running even if the background process is suspended. The service has no user interface, and it uses a small memory. So what it means to say is that all the processes, as for example you were saying like an audio application that user wants to run in the background. So in your Android system, the services help to keep running that particular process in the particular background. It will not have any other user interface, and it will be using a small memory in Android. Now we have seen that, and we have discussed that the processes are switching. That means the CPU is switching between various processes. So the context of a process is represented in the PCB. So this is the state of the particular process. So when the CPU switches to another process, the system must save the state of the old process and load the saved state of the new process, and this is called your context switch. So as you can see, you have to save the values of all the contents of your PCB of the currently running process which has been stopped, and then whatever is the new process which has been selected by your CPU scheduler or short-term scheduler, that the state of that process from its PCB have to be loaded onto the CPU registers. So this is an overhead, and context switch time is an overhead, and the system does no useful work while the switching takes place. Now this is an example of two particular processes, say process P0 and process P1. Now there are two vertical lines on the left and the right side, each depicting the timeline for process 0 and your process 1. Now suppose that the process P0 is executing. There is some interrupt and this particular process has to stop executing. So what will happen? Whatever is the state of the process P0, its state is saved onto the its corresponding PCB, which is the PCB 0. Now suppose the CPU scheduler selected another process, say process 1. So whatever was the partially executed state of that particular process, it was in the PCB 1. That state is loaded onto the CPU, and the process P1 starts to execute. As you can see in these two vertical lines, the thickened arrows actually show the execution of a program. So now suppose that this particular process now P2 is executing, and it requires particular IO and hence calls a system call. So obviously this will stop running. its state would be saved in its PCB1, and suppose that now the CPU scheduler again selects the P0, it is in the ready queue, and the partial state of P0 is now loaded onto the CPU registers and it will start executing. So as you can see in this particular figure, the left and the right vertical lines, that the darkened or the thickened arrows, they are not from top to bottom. There are small time in which the switching is happening, that the CPU is basically idle, which means to say is that while the context is switching, say from process P0 to P1 and then from process P1 to P0, this context switch time, while this is being done, this CPU is idle. So that's why your process switching or the context switching is basically, it's an overhead, it wastes time. But again, this is also required because we require it for achieving your multi-programming. So for more complex operating system and the underlying architecture, your PCB is going to be more complex. So obviously if you have more information on the PCB, the longer would be the context switch. Now this time is also dependent on the hardware support. Now sometimes even with your limited PCB information, or you have extended PCB information, if there is sufficient hardware support, which means to say is that, for example, your hardware could provide multiple sets of registers per CPU. This allows multiple contexts to be loaded at once, which basically means to say is that ideally you have just one set of registers per CPU. But if you have multiple set of registers per CPU, then you could have multiple processes whose context can be saved in these multiple registers. So this is the extended support that a hardware can provide, but obviously this is not there in all the operating system or all the operating systems on the hardware on which they run. The next comes is, we have been talking about the process going from various states, from one state to another state. So the operating system must provide a mechanism for, say, creation of a process or termination of a process, or there are certain other operations of we want to do on a process. So when we say that we click, say, a particular icon which is on my screen, so basically what we have done is we have created a particular process. So underlying in the operating system, we basically have certain specific instructions which help to achieve these operations of process creation and termination and so on. So a parent process creates a child process, or it can create many child processes. The process which is creating another process is called the parent, and the process which has been created is called the child. So these in turn, the child processes, they in turn can create more processes, and what you get is a tree of processes. Now the processes are identified and managed by a unique process identifier, or PID. We just discussed that earlier. Now the options for resource sharing of parent and child processes. Now we just said that the parent basically creates a child process. So what happens to the resources that the parent has? So the different options are that the parent and child share all the resources. Now you need to understand that when a child process is created, it's totally a new process. So it will have its own PCB, but then there are common data like what the code or what is the data. That kind of information is something which can be shared amongst the parent and the child. Another option is that the parent shares a subset of the child shares a subset of the parent's resources and not all of them. And an alternative is that the parent and child share no resources. Now how would the parent and child execute while after the parent has created a child? One option is that the parent and the child processes execute concurrently. So that means they are simultaneously executing. Another option is that the parent can wait until the child terminates. So all these particular options that we are talking about, that the parent runs concurrently or that the parent waits until the child terminates, there are specific instructions that have to be there in the operating system. Another criteria that we have to consider when a child process is created, see what is the address space of the parent and the child process. Now by default what happens is that whenever a parent creates a child process, the child gets a duplicate of the parent's address space. That means the child has been allocated, since it's a new process, it's been allocated a CPU, it's been allocated its own resources. There may be some or all resources which it is sharing with the parent, but then at least the PCB and some specific information like specific data are specific to the child. So the child basically initially by default duplicates whatever is the parent address space. Now in certain scenarios you may want that the child process run a particular program which is different from what it had to run. So in this case the child process has a different program loaded onto it. So as we will see subsequently, there are different specific instructions which basically allow the child to call a particular or load a particular program. So here is an example of process creation in Linux in which you have a tree. At the top is your init process. This is init process is the first process that runs when the operating system is loaded. Is the first process that runs is the init process in Linux. This further then spams other child processes which again call other processes. Now to manage your processes in Unix, this is a particular example we are taking for Unix. We have a particular system call, or we have system calls. Now to recall what are system calls, these are privileged instructions which ensure that the special instructions which are special codes which should be working on the hardware, they run only in the kernel mode. So if a user program needs to call these privileged instructions, they will do it through your system call. So the system call for process creation is your fork system call, which creates a new process. Now this fork returns a particular ID value. That means it returns an integer value. What it is, we'll just see subsequently. Exec, there are similar and there are other similar calls like execlp, execv. It is used after a fork to replace the process's memory space with a new program. So as we were just discussing previously, the child process can call the exec system call when the child process wants to load a different program. That means it wants to run a different program. We have a wait system call or a wait PID. So these are used to when the parent wants to wait for the termination of a child. Now the status, as you can see here, basically means what is the status of the child which has terminated. So that is returned back. In wait PID, the parent can basically, or the parent who calls the wait PID system call can specify which particular child does it want to wait for, and hence the corresponding status of that particular child on termination is sent back to the parent. Now the status could be something like, is it a successful completion or is it abnormal completion? Based on the status we can decide that. Now if we the first system call, which is wait status, is called, basically in that case if you're not specifying which particular process the parent would wait for, then whatever is the first child which terminates, the wait for the parent stops and it will then resume its execution. So the parent either blocks, gets the child return code, or exit status if there are no children. And finally, to basically terminate a particular process, so we use the exit and this exit system call will basically terminate the particular calling process. So the process which has called the exec would terminate, and in that in our code we can specify what is the status. Usually, for example, exit 0 is given when it is a normal termination, and we have a exit code of 1 or 2 corresponding to some code that has been decided in our program, that 1 means that it is error 1, exit code 2 means that it is error 2. Apart from these, we have two very important system calls that we use extensively. One is your get PID and the other is get PPID. Now get PID, basically this system call returns the process ID of the process which called it. So if I have a particular process which is running and I at any point of time want to know what is the ID of this particular process, I will call get PID. In a similar manner, I have get PPID. This system call returns the process ID of the parent of the process which calls it. So if in a program, for example, I have multiple fork statements, so you have a parent which creates a child, now that child becomes a parent for another child process, and so on. So by this mechanism, at any point I can actually get to know what was the parent, what is the grandparent, what is the grandchild in that particular hierarchy of process creation. So this example, as you can see, you have a fork system call. The fork system call basically, now remember, after the fork system call, you have, if the fork is successful, that means the child process has been created. Okay, so now after the fork system call, you have two processes, one is the parent and the other is the child. Now assuming that in the child process you have a exec system call and in the parent you have a wait. So in this scenario, after the parent forks a child, the child basically process executes a different program via the exec system call, and once it has completed its execution, it will call the exit system call to specify that it has exited. The exit status that you had mentioned in the child process, it is returned to the parent process in the wait as a parameter, and we can always see this value. The wait will also return the ID of the child process which has terminated, and after the wait is complete, that means the child process has terminated, the parent can resume its task. Now in a scenario when the parent does not call the wait system call, so after the fork system call, the parent resumes its task and the child resumes its task whether or not it calls the exec system call. In that scenario, your parent can actually terminate before your child. So the fork system call returns a value, and upon success of a fork, so when the fork is not successful, a negative value is returned. Now after fork, since there are two processes, the return value should be able to distinguish which is the parent and which is the child process. So that is why the parent process receives a positive value, which is the PID of the new child created, and the child receives a PID value of 0. So this is extensively used and very useful when we do programming to determine what is the parent process and what is the child process. We use the return ID of your fork. So here's a very basic code, not a complete code, just a skeletal code. We have a fork system call. The return value is taken in a variable PID, and as discussed, PID less than 0, that means fork failed. If your PID is greater than 0, so it is the parent who receives a PID greater than 0, and this PID is the PID of the newly created child. And if your PID, that is the return value of fork, is 0, so that means I am in the child code. So in this way, we can actually distinguish what is the parent and what is the child. So process termination, as we discussed, the process executes the last statement and asks the operating system to terminate it. We use the exec system call. Some operating system do not allow the child to exist if the parent has terminated. So that is, if a process terminates, all of the children also have to be terminated. This is called cascading termination, and this is initiated by the operating system. Alternatively, parent process may wait, as we discussed, for the termination of the child process by using the wait system call. And this is how it is done. You have a PID and it returns a status. The call returns the status information and the PID of the terminated process. So a process which has finished the execution but still has an entry in the process table to report to its parent process, this is called a zombie process. So even if the child process finishes, the entry in the parent the process table would maintain. That child process, though it is in the terminated state, it is called a zombie process because its entry is still there. So a child process always first becomes a zombie before it is removed from the process table. It is in the terminated state. So the parent process reads the exit status of the child process, that means which is now in the zombie state. The entry of the child process is then removed from the process table. So once the parent reads the exit status, then only the zombie process can be removed from the process table. So if the parent terminated without invoking the wait, then the process is orphan. The child process is an orphan. In that case, because the status has to be returned to some process, that orphan process is basically assigned to the init process. We are talking about the Unix environment. So basically, what did we discuss? We discussed briefly about the operating system and some of its system components. What was the need of having operating system processes, and what are the states of the process, what are the process control blocks, what are the different types of schedulers that we have for processes, the creation and the process termination, the operations for creation and process termination, and in the end we concluded by all the system calls that we use for process management in Unix. Thank you.